columns and the beams are all equal to 250. Okay, so you don't worry about the plus moment for different members, especially at the connections. But the possible location with a plus hinge, okay, the possible locations with plus hinge are very large. For example, here we can have plus hinge for section 1, section 2, section 3, and for this joint we can have 3 possible sections. Okay, and so this is a joint with 3 members. So we can have a 1, 2, 3, and maybe just a 1, maybe just 2, and maybe all 3. Okay, so we have to analyze different cases. But of course, in the examination, I will, so don't worry about that. In the examination, I definitely will provide you the location of the plus hinges. Okay, I will not ask you to try different cases because this is very time consuming. So don't worry about that. Okay, although looks very difficult. Okay, so this is the first case, but you just need to understand some rule. The first case is a beam mechanism just for left frame. Okay, so for left frame, please understand the plus hinge. Okay, the plus hinge just at the left beam. So the interior support as an interior column and the right beam still keep rigid connection. Okay, still keep rigid connection. So please understand. And because so in this case, even the plus moment for the column is less than the plus moment for the beam, you still have to take the plus moment for the left beam, because now the plus hinge is at the left beam. Okay, it's not at the column, it's at the left beam. And the connection between the column and the right beam is still rigid connection. So, only beam. So you just need to take the value about the value of the plus moment for the left beam. Even it is a larger, it is a less than, so it is a larger than, okay, it's larger than the plus moment for, larger than the moment of the, larger than the plus moment for other 2 connecting members. Okay, so you just need to take the plus moment for this plus hinge equal to the plus moment for the left beam, even it is larger than the plus moment for this column and for this beam. Okay, so that's all. Okay, and then it is same as single span, single bay. Okay, single span, because we know this idea, because for continuous beam, okay, so plastic analysis is easier than elastic analysis. You just need to analyze span by span. So for the multi-bay or multi-span column, we follow the same way. You just need to analyze span by span. Okay, so this is the first case, and this is the second case. In the second case, you just need to take the moment, the plus moment for this plus hinge equal to the plus moment for the right beam, okay, even the plus moment for this beam is larger than the plus moment for the other 2 connecting members. That's all. Okay, that's all. So if I show you the location of the plus moment, it is not so difficult, okay, to get the solution, okay, because this same as a single span, okay, beam mechanism, okay, and this is a sway mechanism. But please understand, in the sway mechanism, okay, the 2 segments, the left beam and the column and the right beam keep rigid connection. So here beam is a continuous at this point. Okay, so the rotation is a relative rotation between the column and the horizontal beam. So the 2 beams, okay, still keep rigid connection and they keep horizontal. Okay, so in this case, totally we have 3. Okay, we have 3. We have a 6 plus. We have a 6 plus hinge. The moment, the plus moment for this point, and this point definitely equal to the plus moment of the columns. Okay, but for this point, the plus moment must be the lesser value. Okay, so for the joint connecting two members, we always take the lesser value. Okay, and for this point, of course, same as this point, so we take lesser value. But for this location, because the beam is still continuous at this point, so we have to take the moment for this plus hinge equal to the plus moment for the interior column, even, okay, this value is larger than the plus moment for the beam, okay, okay. So in this case, because there is no plus hinge at the beam, so you can only take the plus moment equal to the interior column, okay. So sometimes, okay, the plus moment for this point is different from the plus moment for this point, okay. So please understand this point. So any problem? Okay, so we can go ahead. So here is equal to the plus moment for the column, and here for this point and this point, you just need to select the lesser value. Okay, just need to select the lesser value between the plus moment of the beam and the plus moment of the column. Okay, in this case, okay, totally same, because you don't need to distinguish between the plus moment for beam and column, because it is a constant value for all members. Okay, constant value for all members, and this is a combined case 1. Okay, in combined case 1, you have to at least assume one connection is a radial connection. This is same as the combined case for simple frame, okay, for single span frame structure, okay. But now in the combined case, we can introduce one or more plus hinges at one location. So here we assume 2 plus hinges, okay, 2 plus hinges. I show you how to obtain the rotation angle. Actually, because the plus hinges location are provided, so I will provide you a figure like this. Okay, a figure like this, so you know the location of the plus hinge. So the only thing is you have to, okay, give a correct plus moment for each plus hinge. And then the more important thing is you have to count the rotation angles correctly. Okay, so here is a single, this is a 1 theta, and here's a 1 theta, and here's a 1 theta, because the right beam is horizontal, so for this rotation is also 1 theta. Okay, and here, okay, for this column, the rotation is equal to 1 theta, and for this beam, because the right side is horizontal, so just rotation by 1 theta. So for 6 plus hinges, the rotation angle is just 1 theta. And for this point, because there are rotations for the left segment as well as right segment, so the total rotation is equal to 2 theta. So in this question, 6 plus hinges have, okay, rotation angle equal to 1 theta, and 1 plus hinge has plus moment equal to 2 theta. The rotation equal to 2 theta. So this is a solution, okay, for combined mechanism 1. And then we go to combined mechanism 2. Okay, in combined mechanism 2, again, here we assume, okay, 2 plus hinges. One is at the column, the other one is at the right beam. Okay, right beam. So for the location here, here, and here, okay, as well as this point, and this point, and this point, for the 6 plus hinges, okay, so rotation angle is equal to 1 theta. And for this point, because there are rotation for the left segment and the right segment, so total rotation angle for this plus hinge is equal to 2 theta. Again, for this plus hinge, okay, there are rotations for the beam as well as column. So the total rotation is equal to 2 theta. So 6 plus hinges have rotation angles equal to 1 theta for each. Okay, and the 2 plus hinges, okay, have rotation angles equal to 2 theta for each. Okay, so this is a solution. Okay, this is a solution. So as most important things, how to count the rotation angles, 1 theta or 2 theta or 3 theta, something like this. Okay, and then we go to the combined maximum 3. In this case, we assume the plus hinge here is at the left beam. Okay, and the interior column and the right beam keep visual connection. Okay, keep visual connection. So how to count the number of rotation angles for the case like this? Okay, so for this point we have a 1 theta, 1 theta, 1 theta, and here is a 1 theta. Okay, so for this location and also for this point, the rotation angle is equal to 1 theta because the left beam is assumed horizontal. Okay, so for 5 plus hinges, the rotation angle is equal to 1 theta, and for this location, okay, it is equal to 2 theta, and here is equal to 2 theta again. I don't think it's very difficult to obtain the rotation angles, but we always have some student fail to get the correct solution for the question like this. Okay, I promise you again, I will provide a figure like this if we have a question like this one. Okay, so we can obtain the load factor, and here is a combined case 4. In this combined case, we have assumed 2 radial connection. The first radial connection is between the left column and the left beam. The second connection, radial connection, is the interior column and the right beam. So we can have, for multi-span frame structure, we can have several radial connections. Okay, several radial connections. And again, we can obtain the rotation angles. For example, here is a 1 theta, here's a 1 theta, here's a 1 theta. And for this point, here we have a rotation, here we have a rotation, so the total rotation angle is equal to 2 theta. And for this point, okay, the left segment, the right segment both have rotation. So here again, this is equal to 2 theta. And again, for this point is 2 theta, here's a 2 theta. So 3 plus hinges have rotation angle equal to 1 theta, and the 4 plus hinges have rotation angle equal to 2 theta. So we are able to obtain the load factor. Okay, load factor. And so here we just analyze several cases, and finally, you just need to compare the result obtained from all cases. The smallest one is equal to 1.33, is equal to 1.33. Okay, if my understanding is correct, it's corresponding to the combined maximum 1. Okay, and of course, if you want to confirm it is a true combined is true correct maximum, you have to do the moment check. Okay, so you have to calculate the moment for this section, and also you have to obtain the moment for this section. Okay, I think it is very, you don't need to worry about the multi-span frame structure. It is, when you do the moment check, it is exactly the same as a single span. Okay, for example, if you want to do the moment check for the moment here, you just need to introduce a virtual displacement like this. Okay, a virtual displacement like this. You don't need to introduce horizontal displacement. You just need to introduce the virtual displacement like the beam maximum for the left frame. Okay, so this is a hinge, this is a hinge. So it's very easy to obtain the moment for this section. Okay, moment for this section. That's all. Okay, that's all. Okay, and also you can calculate a moment for this section. You just need to introduce a hinge here, and then you can provide the rotation. We can provide the virtual displacement like this to obtain the moment for this section. So for multi-span frame structure, okay, as a multi-span does not, okay, increase to make the problem more complicated, more difficult. Actually, it's same as, okay, it's a single span structure. So this is a final solution we have obtained is equal to 1.33 years.
For mechanism 2,
Mm-hmm.
why we have 8 hinges instead of 7?
What maximum 2
Right, we have 2.
here?
No.
It's a combined maximum 2.
Yeah.
Yeah,
We
so
have 8 hinges.
So what-
Instead of 7. So 6 minus 2 equals 8.
what is the problem?
2 times 2 is 4. 4 times 6 is 10.
This is a 1, 2, 3, 4, 5, 6.
7, 8.
And then this is a 2, and here's a 2.
Right, but all the
Yeah.
other situations have at least 7 hinges.
This is definitely okay for multi-maximum because for different maximum, the required number of plus hinges is different. For example, for sweep correct maximum, we just need to have 2 for the 2 columns. For example, for single span frame structure, 2 plus hinges are enough for the sweep collapse. But for the beam collapse maximum, you have to introduce 3. So what is your? It is not a problem.
Right
Yeah.
hand side should be 2000.
Oh.
I think 2000 is the height.
You talk about the results here, right?
Right hand side. The 2005.
2000. Here is a 2005. Is incorrect or correct?
Should be 2000.
2000 something. Okay. Okay.
Oh,
check.
no. 2005.
Yeah.
Right.
2005 is correct.
It's correct.
Okay. No problem. Okay. So and then I just mentioned you can do the moment check. Okay. This is a result from the textbook, but I find some problem because the moment I don't know what's the meaning of this moment. This moment is equal to 250. 250 means this is a plus hinge. Okay. So what this value means the moment. So I hope you can do the moment check by yourself. Okay, please try to do the moment check corresponding to this is combined maximum 1, right? Combined maximum 1. Okay, it's no problem because this is a plus hinge already, so the moment should be equal to 250. It's correct. Okay, and the moment for this section must be less than the plus moment. So I try to find this moment. The moment is equal to. Oh, the problem is here. The problem is here. And why here is a 250? I don't know. Please check by yourself because if here is a 250, that means there is a plus hinge here. Okay. So I'm not sure why as a moment diagram given in this way. Please try to check the moment for this point. Okay. Please try to check the moment for this point. You just need to cut off this section and then introduce a voltage displacement like this. Okay. Please do it by yourself. Okay. And also you can check other cases. For example, for combined maximum 3, we know the load factor from this maximum is equal to 1.5. Is larger than the lowest value. So definitely it is not a true collapse maximum. But based on this value, okay, even we know this is not true value of the load factor, but based on this value, we can still estimate the range of the load factor. So now I show you how to obtain the range of the load factor. Okay, so firstly we go back to the combined maximum 3, and we set the load factor equal to 1.5. So we can go back to the combined maximum 3, and then to obtain the moment for this cross section. Okay, we can check the moment for this cross section, and definitely the moment check will be violated. Okay, will be violated. So the moment must be larger than. So for example, for this section, because this is a force application location, And in this combined case, we assume this is not plus hinge, so the moment should be less than a plus moment. But based on the moment check, we obtain this value is larger than 250. Okay, this is reasonable because this is not true case. So definitely, at least one section, we will have moment larger than the plus moment. But based on this value, you can estimate, because this value is obtained according to the combined maximum 3 with lambda equal to 1.5. But because the obtained moment is larger than the plus moment, so the load factor 1.5 must be too large. Because this load factor produces the moment larger than the plus moment. So you have to reduce the true value must be less than 1.5. So how to estimate the low bound? We know this is up bound. The low bound, you can obtain the low bound by multiply the obtained load factor from this maximum by one factor. This factor is equal to the is according to the physical meaning, this is a reduction factor. It's because the maximum allowable moment is equal to 250, but you obtain the moment equal to 375. So if you want to make this is a true case, you have to reduce the load factor to make the maximum moment equal to 250. So if you want to make this value from 375 to 250, you just need to multiply the load factor by the ratio between 250 and over 375. So in this way, you can reduce this moment from 375 to 250. So this is a low bound. But why this is low bound? Why this is not true value? Because the plus moment corresponding to maximum 3, is based on the assumption with the plus hinge here. So this is a plus hinge when the lambda is equal to 5. But when you reduce the lambda from 1.5 to 1.5 times the reduction factor, of course you can control the moment to the maximum moment equal to plus moment. But when you reduce the load factor, the moment at point here may be also reduced. So the original plus hinge becomes not plus hinge. So that means this is not true value. So it is impossible because because when you reduce the load factors of local rest force is reduced. So under the original correct force, this is a plus hinge because the moment reaches the plus moment. But when you reduce the external force, the moment for this section also is reduced. So the moment may be less than the plus moment. So if your original assumption with the plus hinge here is not valid again, So maybe this is not true case. So it is just the low bound. So we can estimate the low bound and the up bound. The true value must be between 1 and 1.5. We know the true value. True value is 1.33. So 1.3 is 33 is equal between 1 and 1.5. So this way, this example provides you a way. Even you do not obtain the true value about load factor, you obtain the load factor from incorrect maximum assumed. But you can still estimate the range of the load factor. The load factor. So this is an example.